Now, what was the substructure of this thing and this thing? Where did these things come from in terms of geometry? We just saw that they came from the g prime over g. In other words, the metric coefficients, the coefficients in front of the dx squared, dy squared, the r squared, the theta squared, etc. All right? So here you have a spatial metric, and here you have a space-time connection. This connection, gamma TR, which would come from a space-time metric. Now the question is there really a space-time metric? In differential geometry, if you have a full theory, one would maybe expect that if you have these, maybe they also come from metric. So we speculate that maybe there is a metric. And so this connection, gamma TR, really comes from a metric in the same way that these gammas, the r theta and the r phi, come from a metric. Except that this metric is a purely spatial one, whereas this metric will be obviously a space-time metric, with at least these two dimensions TR. We're talking about like a two-dimensional system. Okay? So you're going to have some kind of space-time metric with some kind of dt square and like dr square in it, plus, minus, whatever. This is just very naively, heuristically, it looks like there's going to be something like this that you will be able to write a metric in space-time. And there's going to be, you tell me, what is, if gamma TR comes from a metric coefficient, just like gamma r theta comes from a metric coefficient. What can you tell me about this? What do you think? How can I more correctly write that to reflect this? Okay, I'm proposing that there's this very heuristic, some kind of a metric connecting up space and time, so I can measure space-time distances between any two space-time points. I'm saying that this has a connection, this space, where this is a metric of, has a connection given by gamma TR, and a gamma, a connection coefficient, comes from metric coefficients, okay, derivative of the metric coefficient with respect to a different coordinate divided by itself. That gives you the gamma, right, for the spatial ones. So I'm going to say, well, this is differential geometry. I'm going to say it's the same formula, basically, for the space-time connections. So, in other words, there ought to be something like this for the space-time coefficients. In other words, could you guess what's going to happen here? Okay, let me start with this example. We had a non-zero connection that turned out to be 1 over r. Mm-hmm. Why was that the case? Where did the 1 over r come from?
The divergence.
Not from the divergence. The divergence has it because of these things. Okay? When we wrote this, what was the connection? What were the connection coefficients? Gamma x, x, y, gamma y, y, x, gamma x, x, x. They were all the derivatives of what? The coefficients. What are the coefficients here? 1.
Just 1. Okay.
So it was 0. That's why there was no connection evident when you do this. But when we wrote ds squared equals dr squared plus r squared sine squared theta, etc., right? What happened? We were taking derivatives of what? Of the coefficient. What's the coefficient here? 1. So this one had nothing. It was gamma r was 0. This one, though, will have derivatives. The derivative of this with respect to r, or this theta, whatever. These ones will not be 0. That's why you have the 1 over r, right? That's why you have these guys, the r theta and r phi. So now what we're saying is we have these guys for a similar reason, because this is a connection on space-time. We're supposing that it means that there's a metric on space-time, which is a very non-trivial thing. It's a new geometrical structure on space-time, which, you know, before we didn't had any idea that there was such a thing. We knew it was metric of space, metric of time, and not metric of space-time. But we're saying that this comes about from a metric, which it didn't have to. It could exist by itself as a connection on space-time without coming from a metric. But we'll say that it does, just like the spatial one does. What does that mean about this now, this space-time metric?
There needs to be some coefficient somewhere.
Exactly. There needs to be a coefficient. So the coefficient, the gamma TR, right, will come, the gamma TR will come from the coefficient of the dt square, the coefficient of the d square derivative over itself. I'll put in a function over here, I'll call it f, some function of r. Why some function of r? Because I have to take the derivative of this, some function. I have to take the derivative of this with respect to this one. That will give me the gamma TR. Just like the r theta was derivative of one with respect to the other.
Okay.
So I'm going to have to take the derivative of this with respect to this. I'm not going to do the gamma RT, so to speak, derivative of this with respect to that. That we'll do another time. So I'm going to leave this coefficient to be 1. All right? So this one clearly has to be a function of what? Of r, so that the derivative with respect to this guy will be non-zero. So already I'm looking at this and I'm saying, I now propose that I'll have a metric of space-time that looks something like this in a qualitative heuristic way. Derivative of this with respect to this is non-zero. Okay? So now I'm going to say that I have a metric of space-time, and I know that it has this new piece in it, this strange thing, some function coefficient of d squared, of dt squared. And the gamma that I'm going to get, the gamma that I knew of, remember I said, we know that space-time has a space-time gamma, we knew about that, right? That was the free fall world lines. That is now going to be this f prime. Now, it's f prime of r over f of r, something like that, right? All right, so we have something new. But from this, I'm now supposing that my metric of space-time has some kind of function of r in there. That's pretty interesting, right? You would not think that the fact that gravity exists and there's tidal accelerations can tell you that time is kind of worked in this way. It has this function in front of it. You can see already why time warping has to do with gravity. Okay, but it's time warping in the context of a space-time, because you need the derivative of this with respect to r. Okay, so instead of f of r, I can put in, once I'm talking about a metric, we use these letter g's, little g's. Those mean the metric coefficient. So here, gxx is 1, gyy is 1, gzz is 1, grr is 1, g theta theta is r squared sine squared. Okay? You got that? The letter G, simply little g
No,
means.
the subscript just said g theta theta. So
Right,
that would mean the
right. G theta theta would be the coefficient of the d theta squared.
Okay.
Okay, g y would mean the coefficient of dy
So this
squared.
would be like tt right here.
Exactly, precisely. GTT, because that's the coefficient of dt squared. But GTT in our space-time theory comes about from gravity. We're certainly going to expect it has a lot to do with gravity.